Hi! In today's lecture, we're going to look at frost diagrams. We'll be briefly introduced as to how to construct frost diagrams, and we'll focus on the interpretation of these diagrams. Let's begin! A frost diagram basically is a plot of Ne naught against the oxidation state, and it graphically illustrates the relative stability of the different oxidation states of a given substance. This is relative to the elemental form of a given element. And what you see here in the y-axis Ne, N here is not the number of electrons, but rather the oxidation state of a given substance. And this is related to the Gibbs free energy of the substance when it is transformed from the zero oxidation state to the N oxidation state. So what do we get from these frost diagrams? Well, we can have a general overview of the relative stability of the different oxidation states of a given substance, and we can also have an assessment of the reducing power and the oxidizing power of a given couple, and we can predict disproportionation reaction and comproportionation reaction of given substances. This is a Latimer diagram for oxygen in acidic solution. So you have the elemental form of oxygen, O2, and then you have the -1 state peroxide and the -2 state in water. And this is the frost diagram for oxygen. As you can see, there are two lines in this diagram, one in red and then one in blue. So this Latimer diagram actually can be transformed into a frost diagram by doing some calculations in the plotting of the different substances corresponding to the different oxidation states of a substance. So for the red one, this corresponds to the Latimer diagram in an acidic solution, and the blue one is derived from the basic Latimer diagram of oxygen. So if we're going to look at this Latimer diagram of oxygen in acidic solution, we can see that you have the zero oxidation state here, and then H2O2, which is -1 for the oxygen. You have H2O2 here. And how do we get the Ne values? Well, these are just products of the oxidation number N and E, where E is the standard reduction potential for the conversion of a given oxidation state to zero. For example, you have here 0 to -1 in the change of the oxidation state, so that is 0.68. So 0.68 times -1, so you have that point here. So this corresponds to that negative 0.68 value of Ne. How about this one? This is 1.78 from -1 to -2. Well, as you can see for water, it is located below the -2 value. And by looking at this value here, 1.78, if you multiply that by the oxidation state, which is -2, that will not give you a value that is between -2 and -3. So this is derived from actually getting the standard reduction potential for the conversion of the elemental oxygen to water, which is 1.23 volts. You learned this from our previous lesson on Latimer diagrams. And if you multiply this by the oxidation number, which is -2, it should give you a value equal to -2.46, which is around this point here. For the different manganese species, we have here the Latimer diagram in acidic solution. And when you construct the frost diagram, each substance must be connected to the elemental state, which is Mn. So this is an example, or this is the constructed frost diagram for manganese in acidic solution. Notice I labeled here the points 0, 0, -2, 0.36, and then you have 2 here. So you have the oxidation states, and then the values here correspond to the Ne values. Again, these Ne values are derived by multiplying the oxidation state with the standard reduction potential of a given substance traced back to the elemental state.